Good afternoon everyone. Today I am going to discuss about the computer organization subject unit 3. So coming to the content, so unit 3 is called the microprogrammed control. So in this we having some contents, that is control memory, address sequencing, microprograms, example, design of control unit. So these are the contents we are going to explain now. So before going to explain these contents, just we are knowing the introduction of this micro programmed controller. Okay, programmed control. Okay, so introduction. Coming to the introduction, the functions of control unit in a digital computer is to initiate sequence of micro operations. In the digital computer, we are providing the functions of the control unit in the digital computer. So control unit means what ma? Already we have the CPU. In the CPU we having the control unit. So in these functions, the functions of the control unit in a digital computer is to initiate a sequence of micro operations. So whatever the digital computer we are using, in this we are having the some functions of control unit that will be initiates the sequence of micro operations. So in the control unit we are going to implement two ways. One is hardwired control, microprogrammed control. So what is mean by hardwired control? So when a control signals are generated by hardware, control signals who is generating, hardware is generating the control signals. Okay, so using the conventional logic design, techniques, the control unit is said to be the hardwired. Okay, so whatever the control signals is generated by the hardware using the conventional logic designs techniques. So we are using some logic designs. So we are using some logic design techniques in order to generate a hardware. So this can be say as a control unit is said to be a hardwired. So we having some key characteristics, that is high speed of operation. So whenever we are using this hardwired control, we are having the speed of operation of the speed is very high and very expansive, relatively complex, no flexibility of adding new instructions. So we don't have any flexible to add a new instructions in that hardware. Okay, so regarding the cost, it will be very expensive and speed of the operations will be high. So these are the characteristics of the hardwired control. So examples of CPU with a hardwired control unit, or Intel 8085. So Motorola 6802, Zilog 80, and any RISC CPUs. So these are the different types of microprocessors. So this Intel 8085, this is one type of microprocessor invented by the Intel company. Okay, and Motorola, this is also a microprocessor. So in every year, so we having one subject in final year. So in that final year grid and cloud computing, we having the complete details of this CPU, how they are increases, how it developed in every year, and what are the microprocessors we are using. So everything will be have in this on that subject. So here we are just telling that it is the example of the hardwired control. Okay, CPU with hardwired control unit or Intel 8085, Motorola 6802, Zilog 80, and any RISC CPUs. So these are the examples of the hardwired control. Okay, so next coming to microprogrammed control. So what is mean by microcontrolled program? Control information is stored in control memory. So whatever the information we are is there, that information is stored in the control memory. So whatever the operations we are performing in the digital systems, everything is storing in the control memory. The control memory is programmed to initiate the required sequence of micro operations. So what will be the use of control memory? The control memory is programmed to initiate the required sequence of micro operations. So whenever the information stored in the control memory stored in the control memory, the control memory is everything will be programmed, and it can be perform some sequence of micro operations in the control memory. In this we having some key characteristics, that is speed of operation is low. So if you see in the hardwired control. So in this hardwired control, what we have learned, the speed operation is high. Okay, so the speed operation is high. So we are in this hardware we are using, in order to generate a hardware we are using some logic design techniques. So that is why we are having some characteristics like high speed operations, very expansive, relatively complex, no flexibility in order to add a new techniques, new instructions, sorry. Okay, so these are the characteristics of the hardwired control. So micro programmed controls having some key characteristics. So in this speed operation is low when compared with hardwired. So less complex, less expansive, and flexibility to add a new instructions. So what are the different characteristics? It is opposite characteristics to the hardwired. So okay, now low operation speed, speed is very low, so compared to the hardwired, because the control information is normally stored in the control memory. The control memory will be programmed that and required to perform the sequence of micro operations. Okay, so that is in this we having the speed operation is very low, less expansive, less complex, less expansive. We can add any new instructions, we can add any new instructions in this micro programmed control. Example, CPU with micro programmed control unit, or Intel 8080, Motorola 68,000, and any CISC CPUs. In the high hardwired, we are use the RISC CPUs. Here we are using CISC CPUs. So this is the difference between hardwired and micro programmed control. So these are the two types we are having in the micro programmed control. Okay, next coming to the control memory. What is mean by control memory? So a control memory, control functions that specifies the micro operations is called as control variables. So control functions that specifies the in the control functions we are specifying some micro operations. Then we can say it is a control variables. When the control variable is in a one binary state, okay, corresponding micro operation is executed. So whatever the control variables we are talking about that, so that variable is one binary state, the corresponding micro operation is executed. For the other binary state, the state of registers does not change. So the active state of control variable, may be either one state or the zero state, depending on the application. So depending on the application, our active state will be defined, which is active when it is either 1 or a 0 state, state 1 or state 0. So for bus organized system, the control signals that specify micro operations are groups of bits that selected the path in multiplexers, decoders, and arithmetic logic units. So bus organized systems, the control signals for the bus organized system. Bus means what? Bus organized system is whatever the images, whatever the systems we are using, the systems are arranged in a bus format. Okay, so bus organized system, the control signals that specifies micro operations are groups of bits that select the path in multiplexers, decoders, and arithmetic logic units. So in this we having control word. What is mean by control word? So the control word is nothing but the control variables at any given time can be represented by a string of ones and zeros called the control word. So what is mean by control word? Whatever the variables we are having, the variables, control variables at any time, whatever the control variables we are having at any time can be represented in the form of string like zeros and ones called the control word. Okay, so control word. Okay, so all control words can be programmed to perform various operations. So we having the control words. So all the control words are programmed to perform various operations. Okay, various operations. Okay, So operations on the components of the system. So computer components of the system, whatever the control words having, that can be perform various operations. So various operations means like addition, subtraction, multiplication, division. So these are types of operations will be performed. So this is the control memory. Okay. So next, micro program control unit. Micro program control unit. So a control unit whose binary control variables, a control unit in a controller unit whose binary control variables are stored in memory is called a microprogram control unit. So control unit means what ma? Control unit means now only we have talked about control memory. So control memory in the CPU we having the control unit. So in this we having the binary control variables that are stored in the memory. So whatever the information is there in the binary format, so that all are stored in the memory is called the microprogram control unit. So the control word in control memory contains micro instructions. So the micro instructions specifies one or more micro operations of the system. Okay, the sequence of micro instructions constitutes a micro program. So we having some sequence of micro instructions, so constitute of micro program. So the control unit consists of control memory used to store the micro program, and control memory is a permanent, that is read only memory. Okay, permanent for read only memory. The general configuration of the micro programmed control, the general configuration of the micro programmed control unit organization is seen in the diagram. We have seen the, this is the diagram. So in this diagram what we having, next address generator, next address, this is the external input, this is the control word. Okay, control word, and here a next address generator, sequencer, control address register, control memory, ROM, control data registers. So okay, this is the external input, this is the control word, and next address information. Okay, so how it works? So CAR means control control address memory, control address register, sorry. So the control memory, this is the control memory is ROM, the control memory is ROM. So all the control information is permanently stored. So in this permanent, whatever the information is there, so that all informations are stored in, all control informations are stored permanently in control memory, that is ROM. Okay, stored in ROM. Okay, the control memory address, control memory address, this is the control memory address register, control memory address register specifies the address of the micro instructions, and the control data register, CDR holds the micro instructions read from memory, where from they read control memory, from they read from the control memory. The next address generator, next address the next address generator sometimes called the microprogram sequencer. So next address generator sometimes called the called the micro instruction read micro instruction, the micro instructions and control registers. Okay, so the next what is that? The next address generator sometimes called the microprogram sequencer. It is used to generate the next micro instruction address. It needs to generate the next micro instruction address. So the location of the next micro instructions may be the one next in sequence, or it may be located somewhere else in the control memory. So this is the, so what is the use of control memory? Control memory ROM is storing all the control information permanently, and control memory address register COR specifies the address of the micro register instructions and micro instructions, and the control data unit, data register CDR holds the micro instructions reads from memory. The next address generator is sometimes called micro operation sequencer. So it is used to generate the next micro instruction addresses. So the location of the next micro instructions may be one next in sequence, or it may be located somewhere else in the control memory. So this is the working of this diagram. Okay. So next, a computer with a microprogrammed control unit will have two separate memories, a main memory and control memory. So a microprogram consists of micro instructions that specify various internal control signals for execution of register micro operations. So these micro instructions generate the micro operations. So whatever the micro instructions we are using, that will be generate the micro operations. It will be fetches the instruction from main memory, evaluate the effective address, execute the operations, return control to the fetch phase for the next instructions. So these are the different instructions and operations of the micro instructions. So next one is the second one, address sequence. So what is mean by address sequencing? So what is mean by address sequencing? So address sequencing in the micro instructions are stored in control memory in groups. So whatever the micro instructions data are there, that can be stored in the control memory, grouply stored in the control memory, with each group specifying a routine. For every group we are having the routine. Each computer instructions has its own microprogram routine to generate the micro operations. The hardware that controls the address sequencing of the control memory must be capable of sequencing the micro instructions within a routine and be able to branch from one routine to another routine. So in this we having some steps to control must undergo during the execution of a single computer instructions. Load an initial address into the control address register when power is turned on in the computer. So this address is usually the address of the first micro instructions that activates the instructions fetch routines. So IR holds instructions. So the control memory, then it goes through the routine to determine the effective address of the operand. So AR address register holds the operand address. So next step is to generate the micro operations that executes the instructions by considering the opcode and applying the mapping process. The transformation of the instructions code bits to an address in control memory where the routine of instructions located is referred to as mapping process. So these are the steps of the execution of the instructions, computer instruction. So this is the address sequencing capability required in control memory, or so incrementing of the control address register, incremental of the control address register, undirectional branches or conditional branches depending on status bit conditions, a mapping process from the bit of the instructions to an address for control memory, facility for subroutine call and return. So these are the sequencing capabilities required in the control memory. So this is the diagram, this is the status bits. So branch logic, multiplex here, multiplex select, and this is the instruction code. We are mapping that in logic, logic. After that we are performing the multiplexes. So if it is go in this side, multiplexes means branch, multiplex means in this multiplexer we are having one router, in this we are having branch logic, that is multiplex select. Here it is clock, and control memory, this is the micro operations and control. What we have said, that what is the use of control unit? Control unit is mainly used to store the control information permanently, okay, and it will select the status of the control memory and it passes to the branch logic. The branch logic will be given to the multiplexers and multiplexers will be taken by the mapping logic. So this is the subroutine register SBR, this is the incrementer, so this is the status bits. So these are the working. Here instruction code, we are giving the code that logic will be mapping. After mapping we are providing the multiplexer, whatever may be addition, division, multiplexer. If I am taking the example multiplexer, so after multiplexer I went for control address register car. So a control address register use of what is the use of that control register address register. So we having to control the register addresses of the registers. So that is why he put me control address registers. After the clock time is occurred, it will be passed to the clock memory and select a status bit and select a status bit. And select say status bit. Okay, so this is the working of this diagram. Okay, so and next coming to the micro instructions in the control memory contains a set of bits to initiate micro operations in computer registers, and other bits to specify the method by which the next address is obtained. So in this diagram, 4 different parts from which the control address register receives the address. So the incrementer increments the content of the control register. Branching is achieved by specifying the branch address in one of the fields of micro operation instructions. So we are having some conditional branching is obtained by using the part of micro instructions. So in the micro instructions we are having some rules, we have to follow that micro instructions. So to select the specific status bit in order to maintain its location condition. So external address is transferred into to memory via mapping logic unit. So we return the address for subroutine is stored in capital register, but value is used when microprogram wishes to return from the subroutines. Okay, so this is the explanation of this diagram. Next, conditional branching. So what is mean by conditional branching? Conditional branching is conditional branching is obtained by using part of micro instructions to select a specific status bit in order to determine its condition. So conditional branching. So which is conditional branching here? So conditional branching we doesn't have here. So in this conditional branching is obtained by using the part of micro instructions to select a specific status bit in order to determine its condition. The stated conditions are special bits in the systems that provide parameter information such as the carry out of an adder, the sign bit of a number, the mode bits of an instructions, and input output status operations. So in the input output status conditions, the branch logic tests the conditions. The branch logic will test the conditions. If met, then branches, otherwise incrementing the CR control address register. If there are 8 status bit conditions, then 8 bit in the micro instructions are used to specify the conditions and provide the selection variable for the multiplexer. For unconditional branching, fix the value of one status bit to be one load the branch address from control memory into car. So this is called the conditional branching. Next, coming to mapping of instructions. So what is mean by mapping of instructions? A special type of branch exists when a micro instructions specifies branch to be first word in control memory where a microprogram routine is located. Status bits for this type of branch are the bits in the opcode. Assume an opcode of 4 bits and control memory of 128 locations. The memory process converts the 4-bit opcode to a 7-bit address for control memory. Okay, so in this we are having the diagram. So this is the diagram of mapping from instructions code to micro instruction address. So in this we are having computer instructions. This is the opcode 1011. This is the address of the opcode, and after that 1011 I am providing the into, okay, 0 0 0 0 0 0 0. So this like, okay, and this is the if I put 1 here, the complete information is coming to down 1011. So okay, and this is the address. So whatever the information is coming, that is the address. And memory, it is a memory bits, and this is the computer instructions performing. So mapping bits here, micro instructions, micro instruction address. So this is the mapping of instruction code in the micro operation, micro instruction address. So subroutines are programs that are used to other routine to accomplish a particular particular task, and can be called from any point within the main body of the micro program. Sequentially, many micro programs contain identical section of code. So in these micro instructions can be saved by employing the subroutines that use both the sections of micro coded. So in the micro operation programs that use the subroutines must have a provisions for storing the written address during a subroutine called and restoring the address during a subroutine return. A subroutine register is used as a source and destination for address. Okay, so in this we are having the micro program example. Third one, micro program example. The process of code generation for the control memory is called microprogramming. The block diagram of the control organization is as shown in the diagram. The two memory units are memory unit, control memory. So memory unit, it stores the instructions and data, and control memory is nothing but stores the micro operations. And we have 4 processor registers: program counter PC, address register AR, data register DR, accumulator register AC. Okay, these are the 4 processor registers. 2 control unit registers, that is control address registers, subroutine registers, so SBR and CAR. So transfer of information among registers in the processor is through multiplexes rather than a bus. Okay, so this is called microprogram example. So this is the diagram. In this diagram I am having the SBR and SAR and PC here. So it is the multiplexing. It is the multiplexing here. So 10 here, 10 0 10. This is the PC program counter. This is the AR address register. This is the memory. Okay. So this is the for this diagram we have given some explanation. So so in this diagram we are having a register or 10 10 10 10. So in this we are having the 10 10 and is the 6 0 bit 0 bit 0 0 to 6 0 to 6. We are if we count from 0 to, it will be a 7 bit. Okay, 7 bits. Okay, and 0 to 15 means it will be counted from 0, then it is counts as 16 bits. So this is the memory. In this memory we are using the bit that is 2048 into 16. Okay, so these are the different things available in this format. Okay, so we can and this is next one, the computer instruction format is shown here. So this is the of 15 at 15 14 11 10 0, these are things will be there. So next one, so in this from 0 to 15, 0 to 0 to 16. So here we have opcode and address registers, and in these fields for an instructions, 1 bit field for indirect addressing, 4 bit code opcode, 11 bit address fields. So these are the different instructions available in this field. Okay, so 1 bit field is the indirect addressing, so 4 bit opcode is a 4 bit opcode, 11 bit address field. So the example will be considered in the following of the possible 16 memory instructions. Add. So for add operations we are providing some opcode, that is 0 0 0 and description AC add accumulator. So for accumulator we are going to add the information. So we are providing the addition operation here. So this is the branch, and we are using the symbols less than and greater than values, and AC is greater than 0 and PC is less than 1. So store, what is meant by store? M of EA used as to AC. M means memory, so that can be stored in the accumulator. Okay, so exchange 0011 AC accumulator in the given to memory EA and memory EA and AC. So this is the symbolic representation of the 16 memory instructions. Memory instructions format for data control memory is shown below diagram. So here we have F1, F2, F3, CD, BR, AD. This like they have arranged. So every size of this bit size of this block is 6 bits. Okay, 6 bits, and in this we are having the 7 here. Okay, 7 bits. 7 to I have provided some number, that is 33322 okay. So this is the micro operation fields. CD is called condition for branching, branch field BR, and AD address field. So these are the different things available in this format. Okay, and next coming to micro instruction format is composed of 20 bits with 4 parts to it. 3 fields F1, F2, F3 specify micro operations for the computer, 3 bits each. So the CD must select status bit conditions, that is 2 bits. The BR field specifies the type of branches to be used, that is also 2 bits. So AD field contains a branch address, this is the 7 bits. We have 5 letters to specify a transfer wave micro operations. The first two designate the source registers. There is a T. Third is the T. The first two designate the source register, and third one is a T. Last two designate the destination register is accumulator of data register. Okay, DR F1 is equal to 100 is equal to DR T attack. So the condition field CD is 2 bits to following 4 status bits condition as shown in this diagram. So this is the diagram, this is the micro operations addition, this is the micro operation subtraction, micro operation multiplications. So this is the AC, this is our AC all or the accumulator. AC is called the AC is called the accumulator. DR data DR means direct register. DR means direct register. F1 is equal to 100 DRTC. Okay, the condition field CD is 2 bits to specify 4 status bit connection is shown below. Okay, so this is the diagram, this is the addition operations, this is the subtraction operations, this is micro operations. So in these micro operations, symbols are we are using plus, here we are using plus. So whatever thing in this every operation is performed the additions. Okay, plus is the addition operation. Okay, so here I am giving the number F1 string that is 010 and accumulator 0 and clear C, and so these are the different operations performed in the addition micro operations. In instruction micro operations, this is the subtraction operations will be performed here. So minus, everywhere we are using the minus, here upper and greater. Okay, so upper and greater or and AND operations will be performed in the micro operations in the product in the micro operations performed in this device. Okay, next one is the multiplication. So in this we are having multiplication operation. So here we have addition, here we have subtraction, here we are having the multiplexer we are using the XOR, okay. At the rate of complement, A C bar means complement, shift left, shift right. So in CPU, in CPC and TAT PC, okay. So these are the three types of operations we have performed: addition, subtraction, multiplication. So next, coming to each line of an assembly language micro programs defines a symbolic micro instructions, and it is divided into 5 parts. The label field may be empty, or any may empty, or it may specify a symbolic address terminate with a colon. So the micro operation field consists of 1 to 3 symbols separated by antenna, separated by commas, and only one symbol each field from each field. INVOP, if NVOP then translated to 9 zeros, only one symbol from each field. If no NVOP, that translated to 9 zeros. The conditions field specifies one of the 4 conditions. The branch field has one of the 4 branch symbols. A symbolic address must also be loaded. The symbol next to be designated to next address in sequence. So the empty if the branch field is ret, okay, and map and reconverted and converted to 7 zeros, okay. And symbol org defines the first address of microprogram routine. org in 64 places the first micro instructions at a control memory, that is 10 lakhs, okay. So this is called the micro programmed control. Next, coming to fetch routine. So to control the memory has 128 locations. So each one is 20 bits. The first 34 bits are considered by the routines for the 6 instruction address, that is 0 to 63. So the can we start the fetch routine at address 64. The fetch routine requires the following 3 micro instructions at the location of 64 and 66, and the micro instructions needed for fetch routines are this is the example example. So AR means address register, implies program counter, and DR means data register, that is data register, and CR is the control address register, DR is the data register, and AR is the address register. So these are the different registers we are having. Every registers is maintaining their own limit, okay, like 0 to 10, 11, 2 to 5, 11 to 14, 0, 1, 6. So these are the different types of variations occurred in the registers. So after fetching the data, so in this we are having ORG. ORG means what? ORG organizing the 64 jump, okay. These are the different functions we are using: read, increment PC, and DRTAB, tab. So that are so these are the different operations we are performing the fetch routines. So this is the design of control unit. The control unit, the control memory out of each subfield must be decoded to provide the distinct micro operations. The output of decoders are connected to the appropriate inputs in the processor unit. The below figure shows that 3 decoders and the sum of the combination that must be made from their outputs. So in this diagram we having the detect, okay. So this is the link, and this is the P1, P2, P3 arithmetic logic with logic shift unit. So load and multiplexer AR, okay. So these are things are we have taken here. So 3 into 8 decoder we have taken. So in this we having the AND operations we are performing. So AND 3 in this we having 3 into 8 decoders. Like that only we have another format of this decoder. So in this 3 into 8 decoder is performing some operations, and sending their information to the arithmetic logic shift unit. Okay, and this will be performing the after that performing that operations is loaded into the accumulator, and accumulator will be passed to the address register, and address register will be loaded and that can be given to the again a 3 into 8 decoder. Okay, so this is the working of this diagram. Next one, the 3 fields of these micro instructions in the output of the control memory are decoded with a 3 into 8 decoder to provide 8 outputs. Each of the output must be connected to proper circuits to initiate the corresponding micro operations as specified in previous page. Okay, so when f1 is equal to 101 binary 5, the second plus transition transfer the content of dr, that is 0 to 10 to AR address register. Similarly, when f1 is equal to 110 and then binary 6, so binary 6 only 4 actually binary was 2 4 2 3 4. Okay, 2 3 sorry 1 1 2 4 1 2 4. So 4 2 means what? 6. Okay, 6 binary 6. There is a transfer from PC to AR symbolized by PC tar, and we having some outputs that is 5 and 6 of decoder. F1s are connected to the load input of AR address register, so that when either one of these outputs is the active information from the multiplexers is transferred to AR. Okay, so this is called the microprogram sequencer. The basic components of the microprogrammed control unit or the control memory and the circuits are select the next address. So the circuits will be select the next address. The address selection is the part of the part called the microprogram sequencer. The purpose of this microprogram sequencer is to present an address to control the memory, so that a micro instructions may be read the executed one, and the next address logic of the sequencer determines the specific address source to be loaded into the control address registers. We having the block diagram of the sequencer in this here. So this is the block diagram. Here we having the L input logic multiplexer into 2 selector. So this is the control memory. Here we having the micro apps CD and BR AD and transmitter and incrementer SBR. Okay, these are loaded. Okay, so this is the multiplexer. So these are the different controls are available in this micro program sequence for the control memory. Okay, so in this so the input logic circuit is above figure has 3 inputs, that is 1 0 1 1 and T. The 3 outputs S0 S1 and L. So variables S0 and S1 select one of the source address, source address for CR, one of the source address of control address register. Variable L enables the load input in SBR. So the binary values of the selection variables determine the path in the multiplexer. For example, S1 S0 is equal to 10, multiplexer input number is 2, is selected and establishes the transfer path from SBR, okay, to CR. Okay, next coming to, so this is the table of the input logic circuit. In this we having BR, input multiplexing and load SBR. So inputs I1 and I0 are identical to the binary value in the value in the BR field. Okay, BR means this is the BR. First one is the BR field. In this table, BR is the first table. Binary register, I think. Okay, BR. Okay, and BR. The bit values for S. The bit values for S1 and S0 are determined from the stated function and the path and the path in the multiplexer that establishes a required transfer. So a subroutine register is loaded with the incremental value of CAR during a call micro instructions. So whenever it is 0, BR is 1, they provided that the status bit conditioner is satisfied, that is T is equal to 1. The truth table can be used to obtain the simplified Boolean foundations for the input logic circuits. So in this we are having some I1, I0, I2, these are the inputs and this is the multiplexer. So whatever the information we are having after calculating between these two drives, our output will be generated. So S1 is equal to L1. Okay, this is the S1, this is the L1. Okay, S0 is to L2, L0, L1, L2, L2, I2, L0. Sorry, I2, L0, and I1 T, and so this is L is equal to, we are having L here, load SBR, load L2 is equal to T of 1 0. Okay, so these are the different input logic circuit table. This is the truth table of the input logic circuit. Okay, so thank you everyone.